Okay.
Oh, did they answer?
Patient, there's usually a... Yep. All right.
Howdy, mic check. Thanks for surviving with our technical difficulties, but guess what, partners? It's still cloudy out here, but it is getting increasingly darker, maybe due to clouds as well. We are dropping in temperature, so thanks for bearing with us. We want to explain how we get the distance and diameters wrangled in to get a total solar eclipse. We're out here in Bandera, Texas, hill country, where the great North American solar eclipse is passing across the surface of Earth. Now, we get the solar eclipses and partial eclipses roughly 18 months or about 2 times per year. And this is due to the different paths that these objects are on. We know that the moon orbits the Earth, and that has a particular angle in which that happens, which is 5 degrees. So the moon orbits from our equator 5 degrees tilted. Then we have what I like to call the dinner plate of the solar system, which the Earth, the sun, and everything in our solar system sits upon. This is what our seclet hula hoop represents. The ecliptic is at a slightly different angle to that in which the moon orbits around Earth. And thus, when these two paths cross, this is when we have the eclipses, either fully or partially. Today, we've got the total, and that's because we're going to be in the deepest part of the shadow, which is the umbrella of the umbra. The penumbra is the edge of the shadow, and just like when you see your shadow down on Earth, there's a darker, deeper part, and that's where total solar eclipses occur. If you get along that edge, you don't get that totality. And this is a game of the diameters and distances. Each the moon and the sun take up about half a degree, which is about your thumb in the sky. And that is happening for the next 1.2 billion years. We'll have solar eclipses because the moon takes up half a degree in the sky, and so does the sun. But my favorite equation of the solar system, conservation of angular momentum, the moon is spiraling away and thus taking up a smaller angular degree in our sky. At the furthest distance that the moon is right now, 655,000 miles away. We have what we call moon apogee or micromoon, which was the full moon last Sunday that we had the full moon. And the sun is 93 million miles away. So much, much different distances as far as relative to Earth. But this is a game of distance and angular size. The moon is only a few thousand miles wide, while the sun is 865,000 miles wide. And so it's much, much further away at 93 million miles, but much larger. But they happen to be just about the same angular size for the next 1.2 billion years here on Earth. So don't hold your breath. Go ahead and catch out those total solar eclipses. Of course, most of Earth is ocean, 80%. So most of these eclipses, when they shadow kisses the Earth, occurs over ocean land. Now, we're also measuring some of the different temperatures. Pasco is an American company that makes a lot of our equipment that we use at Texas A&M University in our physics and astronomy department. We'll get focused in on here. We're reading out the UV index, which has been steadily dropping. When we first started setting up for the day, this value was at 2. Now we're at 0.07. We also have the red light being read out and the blue light. And so we're seeing a decrease in the dropping of blue light, and this is because of the wavelength scale. Blue light is smaller of a size of the wavelength, and red light is actually a large enough size wave to bend around the edge of the moon. So we will see as we get into the total solar eclipse that we'll have just about the same amount of red light, but we'll have a drop in the blue light, and we'll also have that drop in temperature. So this is a Pasco temperature probe that we've seen. We actually hit almost 90 Fahrenheit earlier in the day when the sun was out. And now we're dropping, when we first started the stream, we were about 75 Fahrenheit. Now we're at 73. And so this is part of a national data collection. So the sensor data that we're collecting here, even though we're a bit socked in, as we like to say, will be collected by Pasco and distributed for science. Do we have any questions on the live stream?
None at the moment.
All right, so When the sun is completely blocked out by the moon, you can actually see a lot of the solar detail. Now, we don't usually get to see beyond the photosphere of the sun because of the amount of light coming from the sun, of course. And that light is generated way deep down where photons are being released from fusion, the only place in the universe where we know we actually have hydrogen atoms slamming into other hydrogen atoms to make helium. And through this chemical process, the photons are spat out. Takes millions, potentially even a billion years for a photon to work its way out. When it reaches the outer layer of the sun, the photosphere, it moves at the speed of light and reaches us here in 8 minutes. And the convection cells, which are depicted inside our 3D model here, are churning and are responsible for the different light and dark spots that we see on the surface of the sun due to the different convection cells moving the temperature. Basically, when we see the surface detail of the sun, convection cells are moving that heat, and magnetic field lines are also getting entangled, which is a streamline from the sun. Just like we have our magnetic field, so does the sun. And those particles that are coming from the sun get tangled. And we have the magnetic field here on Earth, where we have aurora, which can happen on large planets and stars too, where you get magnetic fields that trap high energy particles. And those are constantly bombarding us from space. We've also got a little feature of the moon here. Have you ever wondered why we have chunks of the moon here on Earth, besides the Apollo astronauts bringing home samples? Impact craters are mostly responsible for how we get lunar meteorites. You might wonder why we have chunks of the moon here on Earth that aren't catastrophically obliterated. And that's because if you have an impact, like Copernicus crater here is a large impact crater on the moon, the material and the kinetic energy is allowed to loftate material far enough. And if you get beyond the escape velocity, the material can loftate off of the moon, and since we're in the near Earth space of the moon, material falls down onto the Earth, and that's how we get lunar meteorites. Now, the Apollo astronauts, the Artemis mission, will be going back to the moon, and you will notice when you get to see the moon that there's mostly two main materials. Can we angle that down a little? Thank you. Two main materials. The dark material probably pops out to your eye first because it kind of dominates in large circular basins. This is the lunar mare material. This is lunar simulant. So no, this isn't real moon, but this is as good as you can create in a lab. And this material is dark lava that infills from the largest impact basins, like we showed off with Copernicus crater. And lastly, we'll talk about the lunar highlands material, which are the mountains, the bright white material. Same scale size mountains as here on Earth. Comprised of a little bit more calcium-rich material, but shows off the interesting geology that the moon had when it first formed. Okay, so we're coming in on totality. It's getting quite dark. We're going to hope that we can actually see part of it, but it looks like we're completely socked in. So what will happen is the camera, we're going to let it stream, and you'll see it go into darkness as it is. Let's point it maybe just up towards the sky.
Mm-hmm.
Totality. Do we have a countdown?
Not really.
Okay. Let's check our readouts.
Oh.
Temperature hasn't dropped so much. Wow. Okay, everyone.
I believe we have entered totality.
Wow. Oh, it's so dark.
Like, what the heck just happened? Oh my god.
We took more.
genuinely dark.
Careful where you step. You might trip.
Not so much.
Phone can kind of tell.
Wow. Wow.
That you can't even really tell where the sun should be.
Dude,
Right there.
Yeah.
Hmm. Very fine. Too bad we can't see it.
Yeah.
But this is cool too.
It's still badass. How quiet it is.
Yeah, there's a hush. Even the people somehow. All right, we're moving out of it, I think.
Yeah, it feels like it's getting brighter, right?
Well, hopefully somewhere along the line it's not going to be so cloudy. I don't know where would have been a better choice than here, though.
I wish I had a whole fireworks display I could set up right now, man. Like a 4-minute fireworks display, like right in the middle of the day. Oh, right.
It would be beautiful.
Yeah. And everybody said, remember that time he set up all those fireworks at noon and it was so awesome.
Yeah, brightening back up.
Yeah.
Obviously, the equipment's of no value because they're all out in the street. Nobody's renting it.
Yeah,
So
you could
because it's more open out there, you're getting a bigger.
broader view of it, sure. No, that was nice. You couldn't see the eclipse, but you could certainly tell that it happened.
Mm-hmm.
There was sighs of disappointment and so forth, and I told them all, I don't care. No refunds.
I bet they got a laugh out of that.
No refunds. You all have to continue this.
Sun and the moon
Negotiated
performed.
price of free.
Yeah, that's
You
right.
just couldn't see him.
You want to see your reaction the moment of the eclipse?
You got it on there? Whoa, that's a good capture.
All right.
We're delighted.
Well, I guess we're in front of them.
Okay.
My eclipse photo.
We're still
You
live.
hear that rooster going? It's morning. And
Yeah.
The rooster's
Yeah.
going.
Retreat to the community.
Correct.
Mhm.
I wonder if the microphone's still going.
Okay.
Good job.
All right, folks.
That would be awesome.
Out of the darkness and into the light. Mic check 1 2 1 2. We're coming out. All right. Sadly, We were socked in for the totality, but hopefully you saw that drop. We've collected data along the whole way. Let's answer some questions. That was 4 minutes and 5 seconds for our location here in Hill Country. Remember that that was where the two paths of the moon and the sun were able to cross, which happens roughly 1.5 times a year. And the Great Solar American Eclipse is finishing out. Remember that the moon always casts a shadow, and so does Earth. It just needs something to land on. So every so often we get that configuration where we are on the outside while the moon was in between us and the sun. What other questions might we have? Let's check. Looking good. It's getting brighter. So I want to take some time to convince y'all that although this is a Texas A&M adventure out in the middle of nowhere, we always have fun demonstrations for you. Like coming to you this Saturday, we have our Physics and Engineering Festival. So check back. We'll be posting videos from the different talks. We have an astronaut giving a talk, 200 demos set up, turning our entire department into a festival where they'll be set up along 3 levels. You can come, all ages enjoy. Several thousand attendees from the public have been coming for over 20 years for our Physics and Engineering Festival. So stay tuned. We'll be making videos and posting that later as well. But if you can make your way on down to College Station, that'll be Saturday, April 13th, starting at 10 a.m. So we left off with talking a little bit about the material that we get from the moon. So I'll finish looking at that. So again, that dark lunar material, when you get to see now the days leading after the eclipse, you're going to see that crescent moon. A little bit more of the moon filled up each day, where you get to see the dark and light material. The dark material being the lunar mare. This is all what we call basalt, or a flavor of lava rock. The moon is very calcium flavored. And so this is a dark calcium basalt that fills in due to impact basins. And again, this is simulant. So labs create lunar material to study because lunar material is really expensive. And the mountainous material is the lighter highlands that you see. That's kind of the dichotomy that you see with the moon, is the lighter and the darker material. Same scale size mountains that we have here on Earth. Okay, check our questions. Maybe we'll get a little opening. Let's check.
I think.
Checking questions. Okay, folks, we're hoping that we can still get one telescope view. Might be thinning out.
No.
No?
Did you get the sound of the rooster crowing? That was a great touch.
Yeah, we heard the roosters crowing here. So for those that were in the totality line, you would have been able to see some of the photosphere and the corona of the sun. And that is the outermost layer of the sun that's interacting largely with magnetic material. Houston's calling. Is that NASA? No, NASA. We don't have that much of a problem. Okay, it's actually thinning out a little bit of brighter there, but I think we'll sadly be socked in. But take a look for any of the photos that were snapped right during that peak of totality, because you actually see a lot of solar material, high energy particles coming out again from the outermost layer of the sun after those photons have been trapped deep, deep, deep and created in the core of the sun where the fusion occurs. So we'll have to keep an eye out for those fun photos. Sadly, the clouds have dominated here. So we actually didn't see a huge large in the temperature drop, and that's due to those clouds. These are like an atmospheric buffer, which is the blanket of Earth. And so we actually didn't drop a whole lot of temperature here. But in more latitudes that have drier, like the 30-degree north or the 60-degree north locations, probably saw a much larger temperature swing, probably more like 10 to 20 degrees Fahrenheit. We actually barely even dropped because of those nice, moist Texas cloud layers that we've got here. And we'll be collecting how the light per area, the watts per meter squared, coming from the sun, the amount of energy spread over a surface area of Earth. So we've got that data collected. We'll be turning that in. So I guess will be the clouded out data for our Pasco data collection. And then we also will have been measured that change in the UV index, which has been holding at 0.07. And the slight changes in the blue and the red light. So we'll get close to the end of our stream since we're a bit socked out here. Check if we got more questions. Okay, so someone asked the ring of fire. So the ring of fire is actually, that's a good question. So the distance, whether we have a very close full moon or a further out moon. If you remember, sometimes we have supermoons. That's when the moon is closer in its orbit to Earth. It's actually about 40,000 miles closer. That's when we have a eclipse. When it's closer, it doesn't quite block out the full sun. And we need the moon actually more in a micro moon, a little bit further out to match the angular size of the sun. Yes, if you're clouded out, what's the point? That was maybe the question on the YouTube. But if we were above the atmospheric layer, we would be able to see that during this particular configuration, and with the moon a little bit further out, it's about the same angular size. And that's when you can see, instead of seeing the ring of fire, which is just barely not fully eclipsing each other, you're able to see the more edge-on effects and see that outer layer of the sun because they're closer in that angular size. Let's see if we got a final question. Sounds like Texas A&M got to hear part of it. Nice to see those tuning in. You can try all the ones you want, but if you get clouds, it is what it is. Yep, I see a comment that it looks like it was socked in everywhere. It sounds like many places had the clouds. So hopefully somewhere along that line had least amount of clouds and someone had some photos to take. And we'll remind you all to check for our Texas A&M Physics and Engineering Festival coming to you Saturday, April 13th. Until the next live stream, clear skies, hopefully. Thanks, y'all.